Okay, we're going to talk about friction today. We're going to add a force to our free body diagram. And so let's get started right away. Here's what we're going to be doing. And let me zoom all the way out. Whoa, look at that. Yeah, this is. So here's, this is my coffee mug, my NASA coffee mug that I don't use for coffee. I keep all my pens and pencils in here and stuff. Now, what I'm going to do is I'm going to apply a force to this coffee mug, and I'm going to pull it across the table. Wow. And that is your lab for the week, okay? Let's do that again.
Fulfilling our lab requirement.
That's so cool. Yeah. All right. So, yeah. And people say physics is a drag. Oh, yeah. I got a million of them, I tell you. All right. So, let's actually look at this now. We've got a flat plane, and we'll do this for inclined planes next time. I'm just going to do it for a flat plane right here. So here's my situation. Here's my coffee mug. Okay, here's the handle. Okay, and so it's got pens and pencils and stuff sticking out of it. Now what I'm going to do is I'm going to apply a force to the mug. Here's my applied force. And it's going to move across the table with constant velocity, didn't it? I mean, yeah, at first it was at rest. I had to give it a little acceleration, but then what did I do is I pulled it across the table. It moved with constant velocity. So we're just going to say that V equals a constant. We'll deal with acceleration too. But in this situation that I want to introduce friction in, I want to show it like that. Now, so now we're going to follow the procedure that we talked about. I'm going to draw a free body diagram of the coffee mug and show all the forces acting on it. So here's the coffee mug. And we've got force of gravity. Right? Equals mg. We'll just call it mg. Let me zoom in. Oh, yikes. And then we have a normal force, right? The table pushing up on the mug. I mean, if we didn't have a normal force, the mug would just fall to the center of the earth or somewhere. Emmanuel knows about things, you know, falling. See, the problem was that mass, it didn't have a normal force anymore until it hit the ground. Now, then we applied this force to it right here. So here was an applied force. Now, what I've got now, though, is a force of friction. Now, there is an interaction between the coffee mug and the table. Okay, there is an interaction. Part of that interaction is the normal force. Okay, that is the table applies a force that's perpendicular to their surface upwards, and that's going to support the weight of the coffee mug. But if this thing is moving with constant velocity to the right, well, this force has to be balanced with another interaction between the tabletop and the coffee mug. And that interaction is, we give it this little symbol right here, F. And F means the force of friction. Okay? Now, what is friction? Well, if you were to blow this up and look at it under like a super microscope, the surface of the table would not be perfectly smooth. It would be kind of rough, and you'd see, you know, and then, so here's the surface of the table. And then the surface of the coffee mug would also be kind of rough. There's little gaps in there, but, you know, and so here's the coffee mug. And so when you try to pull this thing this way, you'll get little interactions between these surfaces that will allow you to get a force that that is applied to equal and opposite forces to both. Here's the force on the table. Here's the force on the coffee mug. Well, you have a frictional interaction between the two. I think I got them reversed actually. If you're going to pull this to the right, the force of friction on the coffee mug will be like this, and therefore the force of friction on the table top will be in the opposite direction. Remember, for every force, there is an equal and opposite force on another object. There has to be. It's a law of nature. We've never seen an exception to that. Okay? So this is called the force of friction, and now we just add it to our free body diagram. Okay, and if I make this my x direction and this my y direction, I can say, oh, okay, well, if I sum the forces in the x direction equals ma in the x direction, well, I have an applied force minus a friction force equals 0 because I was pulling with constant velocity. And this is just saying, hey, my force of friction is going to be equal to my applied force, right? Just in the opposite direction. Makes sense. And of course, if I sum the forces in the y direction equals ma in the y direction, well, I've got a normal force in the positive y, and then I've got gravity pulling in the opposite direction. And this just says, hey, the magnitude of your normal force will be equal to the magnitude of your weight. Oops, off screen a little bit. Now, the last few problems we've been doing, calculating the normal force was not that big a deal. I mean, it was nice to know, but we didn't really need it. Well, now we're going to need it. And shoot, I only got about 3 minutes left in class, but so I'm going to go right to the answer, but it's going to kind of make sense to you. I mean, what is this force of friction? I mean, how much friction do we have here? Well, doesn't it depend on how big and heavy that coffee mug is? Right? Yeah, it does. What it really does, it depends on what this normal force is. If I were to take this coffee mug and push it down to the table really hard and try to drag it across, okay, what I'm doing is I'm not just going to pull it like this, because that's pretty easy, but I'm going to push down on it now. And now I'm going to pull it across. Oh my God, it's so hard. All right. So, well, here's another thing. Okay. Okay. Now here's what I want you to do. I want you to all put your hands together like this. Okay. And I want you to barely touch your hands together. Okay. They're barely touch. Now I want you to rub them like this. Not much friction, is there? I mean, you could do this all day long and no problem. Now, I want you to increase the normal force between your hands. What does that mean? That means I'm going to press them together. Now do it. What do you notice about friction? More friction. Okay, more normal force. More friction. Okay, now, as much normal force as you can do. Burst into flame. Okay. Here's what I'm going to contend, and we can do a little lab activity and show this, and maybe we will if we have time. Here's what I'm going to maintain. The force of friction is going to be equal, well, it's going to be directly proportional to the normal force. Okay? So the force of friction, if you double the normal force, you're going to double friction. If there's no normal force at all, you have no friction. Okay, now how much friction you get depends upon the material. Some materials have a lot of grip, like here's a rubber eraser, and if I drag this across the table, I'm going to get a lot more friction than if I, oh, here's a light piece of plastic, hardly any friction there. Why? Because this is slippery stuff. Where this is grippy stuff. Now, why is stuff is grippy and other stuff is slippery? Okay, go into material science. You'll make a good living figuring out why this happens. We're not going to worry about it in here. We're just going to say it does. So what I can do is draw a graph. And so friction as a function of the normal force. And what I'll do is I'll get, when I graph this, I have different normal force, measure the friction. It becomes a straight line like this. And the slope of this line is called the coefficient of friction. And we have a name for that coefficient of friction. It's a measure of how grippy or slippery something is. We call it mu, which is like a Greek letter U, but we call it mu, like a little French kitty cat. Mu. All right? So this tells us how much friction we get for a given amount of normal force. So I'm going to put a mu in here. And this only proves that physics is fun. All right.